Today is 3-2. We have what's called Rolle's theorem and the mean value theorem. All right, so this is just really expanding on what we just did the other day when we were finding the critical values on intervals and those types of things. Okay, so the extreme value theorem states that a continuous function on a closed interval AB must have both a minimum and a maximum interval. That's what we did in 3-1. That's what you just had that worksheet on. Okay, both of these values can actually occur at the endpoints, though. Okay, that's possible that would happen. So then we have this thing called Rolle's theorem. So Rolle's theorem is named after this French mathematician guy. He gives conditions that guarantee the existence of an extreme value in the interior of a closed interval. Okay, so if you think about it, really, the only time that your endpoints are going to be both your max and min would be a what? This is my two endpoints. The only way it could both be the max and the min is if it's a straight line, correct? So a straight horizontal line, if we think graphically. All right, so this one is saying basically we're at the point in math, we're not looking at straight linear functions, okay? So we have this guy, Rolle's theorem. He says if f is continuous on the closed interval AB and differentiable, if we had horizontal line, it'd be like y equals 2. Can we differentiate that? Kind of, but the derivative is 0, right? So it technically is not differentiable. All right, so if it's differentiable on that interval, if you can find the spot where f at A is equal to f at B, then there's at least one number C in AB such that f prime of C is equal to 0. All right, let's look at one. So we're going to use this Rolle's theorem. We're going to find the two x-intercepts of f of x equals x squared minus 3x plus 2. Show that f prime of x equals 0 at some point between the two intercepts. So what we want to do, we want to take this function first, and we're just gonna solve it for 0. We're gonna find our intercepts. Find our intercepts, factor, set it equal to 0. All right, so this guy factors to what? Minus 1 plus 2, or minus 1 minus 2. Minus 1, x minus 2 is equal to 0. All right, so then that means that I have 1 and 2. Those are my two x's. Agreed? Set them both equal to 0. Now, f of 1 and f of 2, they were both, this is my first one, second one. F of 1 is going to be equal to 0. F of 2 is equal to 0 if I plug it back in. Agreed? So therefore, f of 1 is equal to f of 2 because they're both 0. Does that satisfy what we just said in Rolle's theorem? The theorem says if f of A, f of B, then they have to be equal to 0. They have to be equal to each other. Then we're going to find something that would be equal to 0. That means there's a critical value in there. So that fits it. So that means we have a point that exists. Okay? And there exists at least one. So let's find that point. So if we want to find a critical value, what do? You just do on that paper. Differentiate, set it equal to 0. Okay? F prime of x will be 2x minus 3 equals 0. Okay, from there, what would that was my derivative already. So if I want to solve this for x, what do I need to do now? Take 3 over. So then x is going to be 3/2. Okay, so that means I have a critical value that exists at 3/2. We want to look at this in kind of a graphical form. All right, my intercepts would be like 1 and 2. This it would look sort of like this. All right, in this case, it would occur here at 3/2. That Rolle's theorem, excuse me, it just guarantees one of them would be. All right, let's look at one more real quick. I have x to the 4th minus 2x squared. I want to find all c in the interval negative 2, 2, such that f prime of c is equal to 0. What am I asking for? I'm asking for the critical values. That's it. Okay. If we look at this guy, we could take it and factor it by Rolle's theorem just to guarantee that we have them there. But if we take it and we factor it, we're going to find out that, you factor out x squared out of both of those, set it equal, you're going to find that it's going to be equal to 0, just as it did in the first. So I'm just going to save this step here. We're good, okay? So let's find our critical values. F prime of x. Go ahead and factor that, or differentiate that thing. What am I going to end up with? Uh-huh. Uh-huh. Okay. Now we'll set this guy equal to 0. I can factor out of 4x, can I? So I can factor out of 4x. That's going to leave me with x squared minus 1. All right? So that's the difference of two squares now. So 4x, x plus 1, x minus 1. So then what's my critical values? And 0. Because if I set 4x equal to 0, divide both sides by 4, you get 0 anyway. Okay. Now, if there's no 4 there, if it's 4x, I have to set equal to 0. If it's just a 4, I don't set that equal to 0. Remember that rule? If it was like 4 out front, then I just have the 1 plus and minus 1s. I only have to set that front factor equal to 0 and solve it if there's an x with it. Okay? So, that would be our critical values. Well, if we go ahead and look at this, what this guy would look like graphically, give you a rough sketch. So we'll go out to 2 in both directions. So this was that's my interval, negative 2 to 2. All right, so there would have to be 3 points in there of some sort, right? Well, this is what this graph looks like. All right, if you would use a graph function, use Desmos or something like that, you're going to get that picture. So did what we just find fit with what it looks like? Absolutely. We got a critical point here, 0, going to 1, and negative 1. All right, so this is just kind of reinforcing what we did the other day. You all right with that? All right. Mean value theorem. It's the next part. This is kind of the new stuff. So the mean value theorem, 3-4, says if f is continuous on the closed interval a to b and differentiable on the open interval a to b, then there exists a number c in ab such that f prime of c equals f of b minus f a over b minus a. Now, what does that kind of look like? A formula. Does it look like something over there on the far side of the board? Looks like what? Yeah. Looks kind of like a slope formula, doesn't it? Because f at b is y2 if b is 2. You know what I mean? All right, so it's basically a slope formula. So I want to draw a picture. I think this is going to make a little more sense. So I just went down to the bottom of the page here. So say we have a function, all right? And I don't know, I'm just going to do it in a closed interval. My function is going to look like that. That's not a bad picture. Use that one, okay? Now, looking at this, my greatest value, max value, is probably about right there. Agreed? And if we differentiate this function at that point, we're going to find the slope of the tangent line. Okay, that was kind of the whole basis for derivatives, right? It's the slope of the tangent line. So it would look, that would be my tangent line. All right, and that's just the slope of f prime of c. and we'll call that point C. Okay. What the secant line is going to be, so I'm going to say that this is on the closed interval from A to B. So I just cut the rest of the function off from A to B. This is A, right here. This is B. Those are my constraints. This would be a secant line here. Now, what do you notice about those two? They would be what? Parallel. Okay. So if I have a closed interval, I can essentially use this formula, right? Essentially find the slope of the overall function, and that would be the same as the speed at a certain point where it's your max point. Okay, so they kind of go both ways. We'll see here in a minute when we do a problem how that's going to help you. All right. So this here then would be the point A, f at A. That's my x, y values, basically. Back to algebra days, you know. This point here would be your B, and then f at B. So what we really did here is this mean value theorem is talking about the secant line from the beginning of the interval to the end of the interval. And with that, what it's really asking. You guys have that picture down. So what this is really asking for is mean value theorem. This is a big thing. Mean value theorem refers to the average rate of change of the function over the entire interval. Okay? All right. So let's look at this on this first one. So given f of x is 5 minus 4 over x, find all the values of c in the open interval 1 to 4 such that f prime of c equals f of 4 minus f of 1 over 4 minus 1. So we want this to be the same as the tangent line, slope to be the same as the tangent line. All right, let me go ahead and put the points on here because I'm going from 1 to 4. I'd have the points 1, 1, and 4, 4. Okay. Now, at my point of 4, when x is equal to 4, what's the value of y? What's the value of the function? 4. What's the value at x equals 1? 1. On the bottom, I'm going to have 4 equals 1, so I'm going to end up with 3 over 3, which is 1, right? So I want to find the point now where my tangent line would be equal to this. Okay? So I want to take f prime of x. We were setting it equal to 0, right? We were setting it equal to 0. Now we want to set this derivative equal to 1, because the overall average speed, the average velocity over this interval is going to be 1. So we want to find out at what point are we actually going that speed. Okay? So if I'm going to differentiate 5 minus 4 over x, I'm going to end up getting that that's going to be 4 over x squared. Okay, I just go ahead and did that for you. All right, so I'll set that equal to 1. Now I need to solve for x. Multiply both sides by x squared. So then x is going to be equal to 2 and negative 2, right? Is both of those points on this interval? One is. Negative 2 doesn't fit in that interval, does it? So that one's irrelevant to us. So this is the winner. So if I come back here, I can even draw on this. Right there is my secant line. That's my average speed over the time of the whole interval. Okay, so 2 is where that would equal that. So right here, that tangent line would be equal to that. All right. Questions?